Welcome back. In the previous lecture, we gave a characterization of the perfect matching polytope. We're going to use that in this lecture to give a characterization of the matching polytope. So here's what here's a wrap up of the previous lecture. We looked at the following constraints. G is our graph. And the constraints, first of all, non-negativity constraints, the constraint that every vertex must be matched, and then also this constraint that for every odd cardinality set U, the number of edges, or the weight of the edges crossing in or out of U, has to be at least 1 for any U with U odd. This is what in the previous lecture we call QPM, and we showed that QPM is also equal to the polytope of perfect matching. But in getting to here, we had also talked about the relaxation of a polytope of just matching. And the motivation for this was simply looking at the triangle graph. And this is as follows: x greater than or equal to 0, x of delta v less than or equal to 1, and then this constraint that x of all of the edges involved in an odd cardinality subset, so not just the edges crossing in or out of this, but all of the edges involved in those nodes, have to have weight at most 1/2 cardinality of U, the floor of this, where U is some odd subset of V. And in this lecture, we're going to show that this is indeed a characterization of the matching polytope, which I'll write again here, the definition. It is just the convex hull of the indicator vectors of any matching. A matching does not have to be a maximum matching, doesn't have to be a maximal matching even. And as a corollary, we're also going to get another characterization of the perfect matching polytope. QM equals PM can also be written as non-negativity and equality here, and then this same constraint on all odd cardinality subsets. So it turns out that the first characterization was convenient for us, but the second characterization of the perfect matching polytope, pardon me, this is PM, and PM is also going to be useful. Okay, so let us now focus on the task at hand, which is to show that QM is equal to PM. And of course, one inclusion is always clear. So I'll just write it here. Actually, let's go to the next stage. So for the proof, as usual, it's very simple to check that any matching indeed satisfies the constraints of QM. So that tells us that PM is certainly a subset of QM. So the bulk of the proof is showing the converse, the opposite inclusion. And now we're going to use the fact that QPM is equal to the perfect matching polytope. And we're going to use this by enlarging our graph in order to find a perfect matching in there, and thereby proving that that the element of QM that supposedly we had must itself be in the matching polytope. Okay, so for the reverse inclusion, we proceed as follows. Let's make a copy of G. We're going to call this G dash equal to V dash E dash. So the dash here means that it is a copy. So here is G. This is my graph G, and it has some edges. And we have something like this, and then what we're going to do is, well, I didn't mean to make it as symmetric as I did, but oh well. It doesn't matter. So that means that V dash is going to be a copy of all of the vertices. This is literally an exact copy. I'm missing something here. This one. Yep. So these are so this is G dash. I'm going to be considering the union of this. So all of the vertices and all of the edges, but I'm going to add additional vertices. I'm going to add, additional edges. I'm going to add all of these edges across. And now this larger graph, I'm going to call G tilde with nodes V tilde and edges E tilde. So again, just to be clear, V tilde is equal to V union V dash. E tilde is equal to E union all the copies, and now all of the V to V dash edges. So I'll just denote that informally as all the V to V dash edges, where V, V dash are in V, V dash respectively. Again, it just means one edge. So this is G tilde, and we're going to use G tilde. And one thing you can see is that G tilde is going to have a perfect matching. Just the dashed edges are a perfect matching. So this is one way. This is how we're going to use the perfect matching polytope. Okay, so now let's take any x in QM. Our goal is to show that this can be written as a convex hull as a convex combination of matchings. We're going to extend x to, so x is in RE. We're going to extend x to x tilde, which is an element of RE tilde. In other words, x tilde is now going to be a weight vector on the edges of the graph G tilde as follows. So first, for any edge that's in E, I'm going to let x tilde inherit that. So in other words, x tilde for any edge that's in E is just equal to xe. So remember, x tilde for every original edge in E, x tilde actually has two edges, E and E dash, and this is what I've written here. Okay, so this is for any edge in E. And now I need to also choose weights for all of the additional edges, the V to V dash edges, the dashed edges in the previous slide that we added. And I'm going to choose these in a special way. So the weight of any edge, I'll call this E from V to V dash. Hope that notation is not confusing. I'm going to assign this the weight of 1 minus x of delta of V for any V in V. Because V and V dash are exactly the corresponding copies of each other, this is, notice that there's no V dash in this definition, but there's no ambiguity, or there's no aspect of this not being well defined. The key lemma from which essentially the main result follows is that x tilde is in the perfect matching polytope of G tilde. And once we show that x tilde is in the perfect matching polytope of G tilde, then our work is essentially done. So let's write this down. The main lemma that we need to prove is that x tilde belongs to the perfect matching polytope PM of G tilde. And as an immediate corollary of this lemma, well, let me write this actually in a different way, because this is actually how we're going to prove it. We're going to show that x tilde is in QPM of G tilde, and hence that implies immediately from the work in the previous lecture that x tilde is in the polytope of perfect matchings. And as a corollary of this, this will imply that x is in PM of G. Hence, concluding the proof. So I'll let you think about this implication. So exercise, prove the corollary using the lemma. And our work here is going to be focused in proving this lemma. So what is it that we need to do in order to prove the lemma? Well, we simply need to prove that the three main inequalities of QPM are satisfied. Let's flip back so that we can see what those are. We need to show we're using this characterization here. So we need to show non-negativity. That's quite straightforward. We need to show that x of delta of v is equal to 1. But now it's important to note that in the tilde polytope, we have a different definition of delta, right? Because we're looking at now cuts in the larger graph. So I'm going to be using delta tilde and delta in order to make sure that we're not confused by that. So if I were to write delta of v, that just means the cut in the original graph G, all the nodes that are incident to v. But if I write delta tilde of v, I'm still looking at that same node v, but now I'm looking at all of the edges in the graph G tilde. In particular, there's only one additional edge that's incident to one node, and that's the edge that goes from v to v tilde. But the same notation I'm going to use for a general set. So delta of u or delta tilde of u. Okay, so let's show those aspects of the claim. So first of all, certainly x tilde is non-negative. Oh, that one is straightforward to check. Now the second, so that's easy to check. But I also now need to show that x tilde of delta tilde of v is equal to 1. Now, why is this true? Well, you can see that this holds exactly by our construction. So let's write out the details just so we can get into the spirit of what G tilde is versus G and what the rationale was in extending x to x tilde. So my claim is that this holds by construction. Now, for any v in V, since x is in QM, again by assumption, then this certainly implies that x of delta of v is less than or equal to 1. Notice that I'm using delta here and not delta tilde. So what does that mean? Here's my edge v, and there are various other nodes. This is my picture of G. And what this inequality here says, the underlying inequality, is that all of these edges sum to less than 1. And we added one edge, which is the dotted edge. And what did we choose this weight to be? So now you can see why what was the rationale behind the extension. The weight of this edge was exactly 1 minus delta of, let's look back so we can see exactly, yes, 1 minus x of delta of v. 1 minus, was the x that I was missing. 1 minus x of delta of v. So by construction, therefore, x tilde of delta tilde of v equals 1. Just to belabor the point, but again, to make sure we're being clear here, delta tilde versus delta is just the difference of adding or not adding this additional dashed edge. Okay, so we have left to show that x tilde satisfies this property for all odd length nodes. So I need to show that x tilde of delta tilde of u tilde is at least 1, is greater than or equal to 1 for any u tilde, which is a subset of v union v dash, which is v tilde, where u tilde is odd. So again, what was our picture here? This is v, this is v dash, v tilde is all of them. So that means that u tilde is, say, something like this, perhaps. So u tilde is some subset of v and some subset of v dash. Possibly one of these is empty. It doesn't matter. We just know that it has to be odd cardinality. So let's say that u tilde is equal to w union y dash. So in other words, with this notation, these two nodes are equal to w, and picking a different color, these three nodes are equal to y dash. I'm using the dash again to help us remember whether the subset of nodes is in v or in v dash. However, I'm also going to take advantage of the one-to-one identification of nodes. So if I talk about w dash, then I'm talking about the bottom two nodes on the right. And if I talk about y, I'm talking about the corresponding three nodes in v that correspond to the three nodes that I've indicated here belong to y dash. Okay, so hopefully that is going to be clear. Okay, so as an exercise, I leave you to show the following inequality. X tilde of delta tilde of u tilde is greater than or equal to x tilde of delta tilde of w minus y. In our example here, w minus y is the empty set, plus x tilde of delta tilde of the reverse, y dash minus w dash. And again, I hope it's clear what y and w dash both mean. So in order to show this, which I leave to you, you should just carefully think about every single edge in on the right-hand side, and you'll see that that edge appears and is accounted for at least in something on the left. So this is just going through the definition and convincing yourself of this. So we have our set u tilde, which is equal to w union y dash. Let's see our example picture one more time. And we had said in our example that this is it. And because we're assuming that u is odd, you'll note that what this means is that we must have w minus y, or y minus w must be odd. So in this example, y minus w is just a single node, and so it is indeed odd as promised. So if one of these is odd, just by symmetry, without loss of generality, let's just say that w minus y is odd cardinality. Well, if now we found a set, so w minus y, note that, again, the non-dashes means that they're in V, and if they have dashes, they're in V dash. So now I'm talking about, basically in this example, w minus y would just be the yellow node. But in any case, this is an odd subset of just V, and because x was in QPM, I know that I have to have, in QM, I know that x of all of the edges, again, this is not a particularly exciting example in this particular situation, because the way I've chosen is w minus y as just one single node, but in any case, we know that in general, it must satisfy this inequality, the floor of w minus y minus 1/2. Whoops. This floor, which is equal to 1/2 of w minus y minus 1/2, again, because it is odd. And why is this? Just as a reminder, this is because x is an element of QM. And this is just a constraint that QM has to satisfy. All right, very good. So now let's see, what does this tell us about x tilde of delta tilde of w minus y? Let me flip back a slide so that you can see why I care about this quantity. I care about this quantity because it is one of the two terms that lower bounds the quantity on the left, which I need to show is lower bounded by 1. As soon as I show that this is lower bounded by 1, then I'm in business. So as you can see, once you've done this exercise here, then it's enough to show that either one of these two quantities, or sorry, at least one of these two quantities, is lower bounded by 1. So this is what I'm trying to do. So let's write out what x tilde of delta tilde is. Again, note the tilde is on the delta. This is now equal to the sum of all nodes in w minus y of x tilde of delta tilde of v. Now what have I done? Delta tilde of w minus y, that is just all of the edges that are going into the set w that have one endpoint outside w minus y and one point inside w minus y. But what I've written down now is all of the edges that touch any one of the nodes of w minus y. So in particular, I'm counting way too much. I'm counting also all of the nodes that, for example, go from a node in w minus y to another node in w minus y, which is not counted on the left. And I can easily fix this by just subtracting twice the weight of all of the edges that have to do with w and w minus y. Okay. But now this is greater than or equal to w minus y minus w minus y plus 1. How did I get that? It's sitting right there on the page. I used just the above inequality, right? Because this quantity is exactly what is sitting right there. And it's what's sitting right there because of the way that I constructed x tilde. So x tilde on this subset, on these edges, coincides exactly with x. So this is equal to, what's underlined here is exactly equal to x, not x tilde, to just x of e of w minus y. And therefore this inequality that I got because x, we assumed, was in QM holds, and therefore I get this. And this is therefore exactly 1. So this quantity on the left is at least 1, which implies that x tilde of delta tilde of u tilde is bigger than 1. And that implies the lemma. X tilde is in the perfect matching polytope of G tilde. And by the corollary, this implies that X is in the matching polytope of G. And that concludes our story. So now we quickly see, flipping back to the very first slide of this lecture, that we have a characterization of QM. And also it gives us this other corollary that gives us a second characterization of the perfect matching polytope, which we'll have an opportunity to use in future lectures. We will pick it up next time.